This is the demonstration video for CSE535 Group 25 Project BraiNet. Phase 1, we completed creating the mobile app interface. Here you can see it on the screen. It prompts the user to enter their username and begin signal acquisition to authenticate with the system. Settings can be configured. The remote and fog server addresses can be set up, and the server preference can be selected. Simply enter the remote IP address and the port number. Server preference can be remote, fog, or automatic. After entering the server IP address, latency is detected for both the remote and the fog servers. Users can perform signal data acquisition, that would be getting EEG data, but in our example, it's simply loaded from the SD card. The user then enters their name and can press the sign in button. The fog server was selected based on the latency test previously conducted. Login was successful based on the EEG data provided by the user. Network delay and computation time are displayed on the main screen. Fog server and remote server can be tested independently by going to the settings activity. This is a tour of the mobile app code. First we see the login activity, then the signal acquisition activity. We see here that the signal data is loaded from the SD card. The fog server versus remote server algorithm detects latency and makes a decision based on that. An HTTP request is sent to the server with the signal data and the username, and the response from the server is detected to show whether it was a successful or non-successful login activity. Phase 2 is the remote server. This screen shows how easy it is to set up and start running. You can point your web browser at the server address. You'll be presented with the main page where you can go to the administration or the login interface. The administration interface allows you to view the user list and delete users and create new users. You can delete a user by clicking on the delete user button. You can create a new user by entering the desired username and uploading the signal, the EEG signal, with the raw values that will be recorded using a headset. The login interface can also be tested from the web by entering the username and uploading the raw signal data. If you test with signal data from a different user, you'll see that the system will reject the login attempt. This is a tour of the server code. The server was written in Python. A Python MATLAB interface is used to interface with the code provided by the instructor, which does the feature extraction and comparison. All the user data is stored in an SQLite database. The different HTTP requests are served by these different functions defined in the server.py file. You can see the create interface, the delete interface, and the login interface. As expected, the login interface will accept an uploaded file of the signal data. It'll then attempt to find the user based on the username, create a signature from the uploaded file, and then compare that signature with the known good signature from the user. And if those signatures match, then login is successful. These are the MATLAB files provided by the instructor. They do feature extraction and signature comparison. This is a raw data file containing EEG signal data. This is what would be provided at user account creation or login. This is an overview of the SQLite database that is used. There's one table that contains the users, and there's three fields: ID, name, and signature. The signature field is a blob type, and it's a pickled storage of a Python object which contains the different signature values that were returned from the feature extractor.
This is Group 25's demonstration of accuracy calculation. You can see that in this folder, we have three folders. One is the backup data. There are hundreds of backup files for our testing data. This is kind of the backup storage for reference. And the other two folders are negative and positive. Their main goal is to store our positive sample and the negative sample. Positive sample means that the files in the positive folder are the logged-in brainwave files. Okay, so if we receive the brainwave from the positive folder, it means that we can log in our application successfully. Okay, and there are some files. Accuracy.py is our main function to calculate the accuracy and the verification of our sample data, including negative and positive samples. And the extract signal underline to .py. This file's usage is to extract the meaningful data from the raw files downloaded from the website TA gave to us. And there are some MATLAB files. These files are from Professor's sample file. So we use these files for our verification of sample data. how to run our accuracy.py. This is very easy, and we also gave it some explanation in the command line. You can see that there are 3 parameters. One is the PST directory. This means the positive directory. The other one is a negative sample directory. And the final one parameter is file extension. The file extension default string is txt. Okay, and then we can look more about this parameters setting. These are our settings. You can see the positive directory. The default value is the positive directory under the local directory. Then negative directory has the same meaning. And then the final one, extension, the default value is txt file. And we just run our accuracy.py. First, it will start the MATLAB engine. It will cost us around maybe 10 to 20 seconds. Okay, it's done. And it will load our sample data, positive sample data and negative sample data. Then it will proceed calculation. It will cost some time, so this video will do the speeding up to 8 times. To 8 times. Okay, it's already started running, so we will speed up. Okay, now you can see the true positive is 69, the false positive is 74, and the accuracy is around 50%. Okay, now we finish our demonstration of our accuracy calculation.
I'd now like to briefly discuss the task list that was provided at the start of the project and what has been completed so far. For phase 1, it was primarily creating the mobile UI, and this was created and demonstrated in the demo video. Task 1 is creating the basic UI. Task 2 was getting the brainwave signal from the SD card. That's done, and the path location is here. Task 3 is creating the pipeline. This means loading the data from the SD card. Task 4 is using the pipeline to connect the UI to query the API. This is done, and the request is made to the server with the data. The response from the server is interpreted. Task 5 is testing the UI. This was done. And phase 2 was primarily setting up the remote server. Task 1 is setting up the remote server and configuration. This is done. And as I described before, the remote server is a Python-based system. Task number 2 is setting up the database. This is done. That was demonstrated. Task 3 is creating pipelines to store and query the data. This was demonstrated as well, with methods to store and retrieve the user data from the database. Task 4 was designing a UI for user query. This is done, and the web interface for that was shown. Task 5 was testing the database configuration and operations. This was tested using the web interface. Phase 3 involved the fog server and the recognition algorithm. Task 1 was setting up the fog server in the same network as the smartphone. This was done. Number 2 was implementing the recognition algorithm in the fog server. We also implemented it in the remote server since it's the same software stack. The sample code was obtained from the Impact Lab, and the MATLAB files that were provided are used in the server interface. There's a Python to MATLAB bridge that's used. Task 3 is sensing smartphone battery level and network delay. This is done, and those metrics are displayed. Task 4 is running the algorithm to determine whether to use a fog or remote server. This is done based on network latency. Task 5 is the end-to-end implementation of the recommendation of the algorithm. This is done, and the desired server is selected based on that algorithm. Phase 4 is obtaining the real EEG data from the Impact Lab. These data were not obtained using a sensor, but were obtained from a real-world database as instructed by the professor. Task 2 is reporting the accuracy of detection. This is done, and that was demonstrated in this video. Task 3 is recording execution times for both the fog and the cloud server. And these were completed, and these metrics are displayed in the app. Tasks 4 and 5 have yet to be completed. The total number of tasks completed are 18 out of 20, which gives a 90%. Thank you.